Now let us quickly overview how to represent any vector in any coordinate system. A vector consists of both magnitude as well as direction, isn't it? And any coordinate system is characterized by a set of three mutually perpendicular unit vectors, which are used to represent a particular vector in the space. Consider Cartesian coordinate system. You already might be knowing that any vector in the Cartesian coordinate system is represented like this. These small ax, ay and az, these are the unit vectors of the Cartesian coordinate system. The unit vector small ax is defined as the vector of magnitude 1 or unit and which is perpendicular to x equal to constant plane. Again I am repeating, unit vector ax is defined as the vector of magnitude 1 or unit and perpendicular to x equal to constant plane at that point. My dear, now you already know that what is x equal to constant plane. If the given point is like this, then x equal to constant plane will be a plane parallel to yz plane as shown in the figure. And the unit vector ax is perpendicular or normal to this plane. The one which is pointing in the increasing x direction will be the positive ax, and the other one which is pointing in the decreasing x direction, as you can see from the figure, is minus ax. So unit vector ax is defined as a vector of unit magnitude and perpendicular to x equal to constant plane at that given point. Similarly, unit vector ay is defined as the vector of magnitude 1 and which is normal or perpendicular to y equal to constant plane at that given. And finally, az, it is perpendicular to z equal to constant plane at that given point. My dear, if these unit vectors are pointing in the increasing direction, then they are taken as positive. Increasing x direction plus ax, increasing y direction plus ay, increasing z direction plus az. And if at that given point, if they are pointing towards decreasing direction, then they are taken as minus or negative. So these are the unit vectors in the Cartesian coordinate system, which are used to represent any vector in the Cartesian system. My dear, you can also remember like this. Ax is the unit vector along x-axis. Ay is the unit vector along y-axis. It is positive if it is pointing in the plus direction. It is negative if it is pointing in the decreasing direction. So you can remember also like this. Unit vector ax is along x, ay is along y, and az is along z. These capital Ax, Ay and Az, the terms or coefficients with unit vectors, these are the components of the given vector. And you already might be knowing that these components may be constants or functions. For example, if given vector is like this, then its x component is 3, its y component is -4, and its z component is 5. You already might be knowing the vector theory in very much detail. But in very simple words, the component of the given vector can be defined as the effect or the flux of the given vector along that particular axis. X component is the effect or flux of the given vector along x. Y component is the effect along y, and z component is the effect or flux of the given vector along z, and the given vector is the combined effect of all these components with specific magnitude and direction in the space. Or you can say also like this, the given vector is the vector addition of its own components as shown in the figure. The similar representation is equally applicable in cylindrical and spherical coordinate system. In a cylindrical coordinate system, any vector will have three components: rho component, phi component, and z component. defined by the three mutually perpendicular unit vectors, a rho, a phi and az. These capital A rho, capital A phi and capital Az, these are the components, and these small a rho, small a phi and small az, these are the unit vectors of the cylindrical coordinate system. But we can define these unit vectors as we have defined in the Cartesian. Unit vector A rho is the vector of magnitude 1 unit and which is normal or perpendicular to rho equal to constant plane at that given point. Similarly, a phi is the vector of unit magnitude and normal to phi equal to constant plane. And finally, az, it is exactly the same. It is perpendicular or normal to z equal to constant plane at that given point. So let us try to draw these unit vectors at this given point. Let us say we are given with the point P like this. So let us draw these unit vectors at this point. Now, my dear, again recall, unit vector A rho is the vector normal to rho equal to constant plane. And rho equal to constant plane or rho equal to constant surface is like this. Just recall the cylindrical coordinate system lecture. It is a cylindrical curved surface, isn't it? So rho equal to constant surface is like this. And perpendicular to this surface at point P, the unit vectors A rho are actually in the figure. We take plus A rho in the increasing direction of rho and we take minus A rho in the decreasing direction of rho. Recall the cylindrical coordinate system lecture. Rho is the lateral distance of the point from the z-axis. So increasing rho direction is as shown in the figure. It is like this. And decreasing rho direction is towards the z-axis, as you can clearly see from the figure. Next, unit vector a phi. It is the vector of unit magnitude and perpendicular or normal to phi equal to constant plane at that point. Now, my dear, just recall that. What is phi equal to constant plane? It is a vertical half plane attached to the z-axis. Am I right? It is like this. And perpendicular to this phi equal to constant plane at P are as shown in the figure. These are the a phi unit vectors. We will take positive a phi vector in the increasing direction of phi and negative a phi unit vector in the decreasing direction of phi. Now, my dear, again recall the cylindrical coordinate system lecture. The normal increasing or positive direction of phi is the anticlockwise direction. Plus x plus y minus x minus y. This is the anticlockwise direction. So normal positive direction for phi is anticlockwise like this. So our plus a phi will be like this and minus a phi will be the decreasing phi direction, will be like this. And last one, unit vector az is exactly the same as we have seen in the Cartesian. It is a vector normal to z equal to constant plane at that point actually. Plus az pointing in the increasing z direction, minus az pointing in the decreasing z direction. So this is how any vector in cylindrical coordinates is represented, using three mutually perpendicular set of unit vectors, a rho, a phi and az, and they are forming three components: rho component, phi component and z component. Rho component of the vector is the flux of the given vector along rho. Phi component is the flux of that vector along phi, and z, it is the flux or effect of the given vector along z. And collectively all these components, collectively they form the given vector with particular magnitude and particular direction in the space. Finally, spherical coordinate system is characterized by three mutually perpendicular unit vectors that are AR, A theta and A phi. And as we have defined the unit vectors in Cartesian and cylindrical, we can define AR as a unit vector perpendicular or normal to R equal to constant plane. We know that R equal to constant plane is a spherical surface as like this. and perpendicular to this plane is nothing but the unit vector AR. We take plus AR in the increasing direction of R, and we take minus AR if it is pointing in the decreasing direction of AR, as you can see from the figure. Unit vector A phi, it is exactly the same as we have just discussed in the cylindrical coordinate system. So it is exactly the same because phi coordinate is exactly the same in both cylindrical and spherical coordinate system. So unit vector A phi is exactly the same as we have just discussed. Unit vector A theta, it will be the normal to theta equal to constant plane. Now theta equal to constant plane is a conical curved surface whose apex is as origin, isn't it? As like this. And perpendicular to this surface, perpendicular to this plane at the given point is nothing but the unit vectors A theta, as like this. Out of these two, we will take one plus A theta, which is along the increasing theta direction, and other one we will take the minus A theta, which is along the decreasing theta direction. Now my dear, just again recall the lecture of spherical coordinate system. The normal increasing direction of theta is like this, from 0 to pi. So this will be our plus A theta and that will be our minus A theta. So this is how any vector is represented in the Cartesian coordinate system or cylindrical coordinate system or spherical coordinate system. Each coordinate system has unique set of three mutually perpendicular unit vectors which are forming three components of the vector. Collectively, all the components together give us a final vector with particular magnitude and unique direction in the space. Cartesian coordinate system is characterized by AX, AY and AZ. Cylindrical coordinate system is characterized by A rho, A phi and AZ. And spherical coordinate system is characterized by AR, A theta and A phi.